So I had a goal to design the fastest,
Gets me every time.
most versatile, and most fun to control robot arm.
Are you driving?
I mean, no, technically it's not.
That's so easy to make, a kid can build one. And when I say build one, I mean everything. The 3D modeling, the wiring, and the coding, all from scratch. Did I achieve that? This is not what I wanted. Now that's fine. Okay, I didn't make it do any of that. And now I can't control it, and that sound is completely, I have no idea what that sound. Will you learn a lot about how to make your own robot arm? Definitely. No one out there has made a robot arm quite like this. Now we know why. So one of my students
I personally don't like electric cars.
asked if we could build a robot arm for our next in-class project. We just finished building the Nerf turret. Oh! And that involved 3D modeling and printing everything, writing the code to control 3 servos with an ESP32 using a PlayStation controller. So I mean, theoretically, we're just adding 3 servos, copy-pasting a code base, adding a little bit more power, and it should just work.
All of this just works. I'm not kidding.
Because the gripper is the most complicated part, I'm gonna start there. Specifically, I want to make this degree of actuation of motion. Now, I've never made a 3D printed gear before, so I downloaded one from the internet, blew it up so you could see it better, and just take a look at it. Watch how well these spin.
Wow.
There's no bearings on here, it's just 3D printed plastic against 3D printed plastic. There's no backlash. The gears are in constant contact with one another, meaning that the motion of one gear is efficiently transferred to the second gear. So I attempted to make my own gears to the same dimensions, and well, they're garbage trash. Look at this backlash, and look at how terribly they spin. So you might say, well, there's an easy fix for that. Just make the teeth bigger to diminish the backlash. Well, let's try that. Surprisingly, even though we got rid of the backlash, they spin even worse. This is because the point of force application between the teeth is not perpendicular to the rotational axis. So some of that force is wasted. So if I want to make my own gear and get all these curvatures down right, I'm going to have to learn gear geometry in great detail.
Face of tooth is the surface of the gear tooth above the pitch surface. Flank of tooth is the surface of the gear tooth below the pitch surface. Profile is the curve formed by the face and flank of the tooth. Fillet radius is the radius that connects the root circle to the profile of the tooth. Face width is the width of the gear tooth measured parallel to its axis. Top land is the surface of the top of the tooth. Bottom land is the surface at the bottom of the gear tooth space adjoining the fillet.
Hi, this is Gascan, and today I'm going to show you guys how to make spur gears in Fusion 360 the easy way. So stuff like this, and up to small stuff.
All right, Mason. We're going to teach everybody how we made the gripper on our robot arm. And to make it simple, I made a giant Easter-themed gripper, which we're going to use to crush a giant Easter egg filled with, you'll find out, and spoiler alert, I don't think this is going to work. You ready to show it off? All right, so we're gonna plug in the battery. It's gonna kick on you. You ready? Good Lord.
Oh.
All right, hit the buttons too.
Think it's got enough kick to it?
Isn't this ridiculous?
Seriously, I see what you mean by the jank.
Yeah.
The
Yep.
speed control.
Yep. I have to fix that.
That's pretty ugly.
Yeah, I have to fix that.
Alright, so I wanted to show you how we modeled this gripper beginning with the gears. These are called spur gears, and just look how beautiful they are. Look how well they roll off of each other with almost no play at all. If you wanted to make your own gears, you'd have to model all these tiny little curvatures yourself. But thankfully you can run a Python script in Fusion, and it makes these nice little spur gears. Now I've modeled all the arms and pincers and animated all the joints, and now look how smooth this moves. Now the important part is that both of these arms have to be the same exact length, otherwise it'll move like this. So as you've seen, both sides move on their own, but we want them to move together. So we use a motion link to connect the two joints, and now look at that. And for the love of God, Will, we'll crack the egg.
Again? Again? Oh my God. Sorry, I gotta work the coding. All right, that's it. I don't care. Yay! We cracked the egg.
Ugh.
You don't want to peep?
No, okay.
So I finished 3D modeling and 3D printing all the parts that go into the build, and I try to make it so simple that my grade school class can make their own. I'm going to break down every single part so that if you wanted to make one for yourself, you'll know how to get started. You've already seen the gripper, and I added a servo at the back of it to create a rotational axis. To make the wrist tilt, I created a housing that encapsulates the entire gripper along with the 20 kilogram servo. When that servo rotates, it pulls the entire wrist along with it. And to keep motion smooth, I have a bearing on the other side where I press fit another 3D printed part against it. I use the same process of encapsulating a servo to make the elbow and the shoulder tilt joint. Now, rotating the entire arm had a unique problem. You see, this pivot point has to support the weight of the entire arm, and there's no way this tiny pivot point can accomplish that. And I tried to think of a way to do this cheaply, and then I thought about it. I could just use a Lazy Susan bearing. I'm going to mount it to the base along with the servo, and that's going to hold the rest of the weight. All right, let's try controlling this using my improved electronics and code base. So this is the same setup I use in my Nerf turret, with the key change that I'm using two 18650 batteries as opposed to 4 AA's. And right now I'm just powering it with the USB, and it works just fine. But if I flip this on and unplug my USB cable, it should just work. So let's go.
Skill issue.
So it's either too much current, too much voltage, or both. I'm not sure. Either way, this chip's not handling it. So I'm going to have to think about a solution. In the meantime, a big point of this video is I wanted to teach everybody the basics of how you can control any robot with a PlayStation, Xbox, or Nintendo controller. I don't think there's many good tutorials to get you started, so I'm going to teach you that. And hopefully I can come up with a solution in the meantime, because I have about 6 kids that are waiting on their robot arms. And yeah. To read the information coming from my controller, I simply run a program that someone else has already written, known as a library. Here, I am running the PS3 demo program, and you can see that I can detect which buttons are pressed, as well as how far I move the thumbsticks. Now, I've deleted all the unnecessary code and only retained the code required to read the right thumbstick and display that as a value called rightX. It blows my mind how little code this requires. Now watch what happens when I move the controller all the way to the left and all the way to the right. If I move the thumbstick all the way to the left, it registers up to -128, and all the way to the right, it registers 127. Now how do I do something useful with these values? Well, I wrote a code that did some basic math. I take the right X value, divide it by 128, and display it as a variable called servo accel. Now watch what happens when I move the thumbstick all the way to the left and to the right. Now when I move it all the way to the left, it registers up to -1, and all the way to the right, it registers about 1. Now it's time to talk servos. Here I've written a code that rotates a servo between 0 degrees and 180 degrees. It does this by gradually adding 1 over and over to the degree variable until it reaches 180 degrees. Once it reaches 180 degrees, I flip it from adding 1 to adding -1 over and over, which means now it subtracts it from 180 degrees down to 0. Well, now let's think about this. I have a program that could read values coming from my PlayStation controller and scale them between -1 to 1. And I have another program that can move a servo by adding or subtracting 1. If only I could fuse the two.
Fusion!
Well, here you have it. Not only can I move the servo using the PlayStation controller, but it has speed control. The further I move the thumbstick, the faster it rotates. Now, I left out a lot of detail on how to go about this, but if you want to learn more, there's a link in the description for my second channel where you can learn how to do all of this for yourself. Okay, so now that you get all the basics, what's the problem with my robot? Well, I use the servo controller board here, which is very commonly used in standard hobby robotics, but it doesn't have the power required to run all my servos at once. On top of that, the way I coded it isn't the best way. There's a slightly more sophisticated way than the way I showed you, which will give me more fine control and avoid the jank. So instead of using this board, I actually made my own. Recently, I had a booth at Open Source where I got to meet some awesome YouTubers. Some of my students even got to be on stage with awesome creators like Nile Red.
William has 6 robots. How many ways can he organize them in a row?
Okay, 180.
Oh, I don't think that's right.
720.
That is correct.
And one of my students, Asher, absolutely blew Destin away with his big brainium.
How many bones are in an adult human body?
206.
206 is right.
What separates the Earth into Western and Eastern hemispheres?
Prime meridian.
Yes!
Tuna fish, frozen ice, and chai tea are all examples of what?
Topology.
Oh, I'll give it to you, a tautology. That's right. All right.
Also, what is that?
At Open Source, there was one company I wanted to connect with, PCBWay, because I knew I needed to make a circuit board in order to make my arm work. I approached their booth and gave them my information to get sponsorship, and I didn't hear anything back, and that's okay. I figured, well, I'm a small channel, no big deal. Well, 2 months later, I get this random message on my TikTok, completely unrelated, and I'm like, you've got to be kidding me. This gave me the courage to finally make my first PCB. It's actually a lot easier than you might think. There's a free software called KiCad that I use to design it. You find the components you're going to use, drag and drop them in place, and wire them. This generates a 3D model of your board, and you can either use a plugin to export it directly to the PCBWay website, or you just drag and drop the files to their website and fill in those fields for yourself. An engineer checks it over to see if there's any obvious errors. You get an instant quote, and making these is a lot cheaper than you might think. PCBWay has been phenomenal to work with, and I appreciate that they reached out to me specifically to help out my students. I can't thank you guys enough. You're my first sponsor.
Much later.
And that brings us to where I am today. Yeah, I got some work to do. See, this project has taken about 2 years, and there's so many other problems that I don't have time to explain, but my students just had to give up and we had to move on to other projects, so that means my students don't have finished working robot arms. So now that I have the PCB, I bought all the extra parts to make them work, and I'm just gonna finish them for them, so it's building montage time. Well, you know my lovely PCB I spent all this time on? Well, guess what? It fits on my 3D printed parts just fine, but watch what happens when I put the Lazy Susan bearing on top of it. See, it needs a screw into there. Now, do you guys see the problem? Do you see it? Do you see it yet? My brain is so smooth, you can ice skate on it. Oh! I'm an engineer. We don't plan, we improvise. Alright, let's see if I wired this thing properly. Okay, good sign. Let's test all the axes. Oh god, gotta get this thing down so let's rotate it. Rotate, shoulder, elbow, wrist, rotate, gripper. Looks good. Okay, now I just have to recode the entire thing from scratch.
4 to 6 weeks later.
So I've finished reprogramming my arm, as well as all of these. As we added complexity, the copy pasta got out of control. So I recoded the entire thing using object-oriented programming. So now I have dedicated classes for my servo, as well as a timer class. This also helped smooth the motion of the arm and give it a satisfying analog feel. PlayStation controller is a very good device for efficient analog control, and as a teacher who also teaches game design, the feel of the robot deeply matters to me. I'm happy with how this turned out, but this took far too long. It's not the coding or the 3D modeling, it's finding the right servo horns, finding the right power supply, just finding the right parts. No one out there has made a robot arm quite like this. Now we know why. Anyway, there's only one way to celebrate. Mondo Cool montage time.
That's right, boys. Mondo Cool.
Thank you for watching, and you know the drill. Like, comment, and subscribe. This points more people to the video, but more importantly, this helps grow my school. During these videos, I only show you brief snippets from my classes because when I teach, my priority is well teaching, so I can't both film and teach well at the same time. I run a homeschool and after-school STEM education center called Advanced Personalized Learning. We teach a range of topics from math to science to robotics to coding video games. Almost universally, our students perform well beyond grade level. We have 5th graders doing algebra, 7th graders doing pre-calculus, and 8th graders doing AP Physics, a subject which I have deep knowledge of, having written an entire textbook on the subject. I have a very diverse background in science, starting off as an electrical engineering major, switching to physics, and then switching again to kinesiology. Then I got a master's in biomedicine, and then I went to medical school for 2 years, and then I decided to leave it all behind because I like teaching. I don't want to be a science practitioner. I want to be a science educator. At our school, we have high school and even grade school kids 3D modeling in Fusion 360, making robots using the Arduino and ESP32, and coding video games from Pong to Cookie Clicker to Flappy Bird, even Mario. A lot of our kids go on to get into the most prestigious high schools and colleges in the country, some of which receive scholarships. We have in-person classes in Northern California, but I also conduct online classes throughout the country. If you want to learn more, email me at thethinkerteacher@gmail.com. All lowercase, no spaces. Lastly, if you'd like to partner and help me grow my school, looking at you, Mark Rober, please contact me. We have a STEM center here, but I want to expand these STEM centers to be across the country, where teachers can meet with their students and teach them college-level stuff beginning in grade school. Lastly, for a preview of what's coming next, check out this AI Photoshop slop concept art.